И запись.
Да, у нас, то есть, да, если вы не против, у нас трансляция в YouTube сразу, и там и сразу и запись будет.
Конечно, да. Нет, я не против.
Вот, да, трансляция включена. Так
что,
видимо, можно начинать. Гаиане Панина про класс Эйлера SN расслоение.
Thank you very much. So I will speak about Euler class of spherical fiber bundles. And let me start with, so I plan to give a very elementary talk. So it is written in the title. So it is elementary approach.
Гаиане, раз этот talk elementary, сможешь ли ты периодически подводить резюме под вышесказанным по-русски, еще повторять?
Yes, sure, sure. I will. If I forget, please remind me. Please keep reminding me. So I will start with a reminder, so to say, and with explaining what we are going to study. So we have a fiber bundle which consists of the total space E, continuous map pi, and the base, which we denote by B. And well, it is convenient if you hear it for the first time. Just imagine that B is some closed manifold, and E is also would be nice to imagine to be a closed manifold. And pi is a projection such that it is the bundle, fiber bundle, which means that for each point from the base, for each point from the base, the pre-image of X is homeomorphic to the n-dimensional sphere, and all these fibers are consistently oriented. So the fibers are all oriented. And we also think that, as usual, this vibration is locally trivial. And we also ask for some additional structure. We assume that the base and the total space are consistently triangulated. This means that, well, they are just the supports of some simplicial complexes. And to be honest, here we need actually some more conditions, but let me sweep them under the carpet. So for the beginning, just let us think that they are triangulated consistently, which means that the map pi maps simplices to simplices. And the pi is linear on each of the simplices, linearly. And so let us start with the following toy examples. The toy example will be the example when n equals 1. That is, we have a fiber bundle whose fiber is just an oriented circle. And so let's look here. This is our base B. And for the moment B, let us think that B is just one-dimensional manifold. And here is the total space E, which projects here. And of course, the preimage of each X should be a circle, but we assume that here the upper part is patched together, is glued with the lower part. Okay, so it's really a circular bundle. Well, next, the base is triangulated, and in our case means that it is cut into segments, and also the total space is triangulated, means that we have something like I have depicted here. So it is so to say, it is a cylinder which hangs above this one-dimensional thing, and it is cut into simplices consistently with this projection. It is exactly what you see here. So we have something like this, so to say. Okay, so this is how a toy example looks like for the dimension of the sphere equals 1. Okay, now what is Euler class? I will give you a definition a little bit later, but for the time being, let us agree that Euler class is a characteristic class. It is some feature of the vibration, and the Euler class, for the time being, it is sufficient to know that the Euler class of a fiber bundle is an element of the n+1 cohomology group of the base. And well, I prefer to write here rational numbers, because our local combinatorial formula will be an algorithm which computes a rational Euler class. Now I repeat the same in Russian. Давайте посмотрим на такой игрушечный пример, когда у нас все слои являются окружностями. И этот игрушечный пример замечательный тем, что его можно вот так вот нарисовать. Значит, нужно понимать, что вот здесь у нас склеено вот с этим. Значит, у нас получается такой цилиндр, который проецируется на одномерную базу B. И вот согласованность триангуляций означает ровно то, что картинка у нас такая, как здесь нарисована. Теперь класс Эйлера. Это некоторый класс, который я пока не определила. Он живет в n плюс первых когомологиях базы. И в данном случае я хочу написать, что коэффициенты у нас рациональные числа. So we have the Euler class, and we have a special task to find combinatorial formula. Task. The task is the following: produce an algorithm. Produce an algorithm or a formula which computes a cochain representing the Euler class. The algorithm should be local. What does this mean? First of all, let me remind you that a cochain, I keep in mind a cochain related, a simplicial cochain related to the triangulation of the base B. And the cochain is a rule which assigns some rational number to each of the n+1 dimensional simplices in the base. So it should be some rule. Given an n+1 dimensional simplex, we assign to it some rational number. And we aim at a cochain which represents the Euler class. So just notice that there are many cochains representing one and the same class, and we need to find one. But the algorithm should be local, meaning the following. That we have many persons, and these persons sit here on the n+1 dimensional simplices. So for our toy example, let me a little bit extend the base B. Let me make it two-dimensional. So on each two-dimensional simplex, there sits a person. And a person is allowed to look only upwards, to look at the preimage of this simplex. So if we imagine that the simplex is this one, then this person looks only at this heap of triangles. And he doesn't know what happens here. And in the same manner, this guy, he is allowed to look only here. And judging by the combinatorics of the triangulation of this cylinder, of this short cylinder, he has to produce a rational number and to assign it to the simplex in the base. and all these rational numbers taken together should give us the Euler class. That's the task. And it is not absolutely clear why such an algorithm exists. Because you see, we assume that our fiber bundle is locally trivial. This means that if not this triangulation, if there were no triangulation here, each of these persons, no matter what is the fiber bundle, sees one and the same figure in the preimage, because in the preimage we always have one and the same from the topological viewpoint. We always have our simplex of dimension n+1 times the sphere, So the preimage topologically is homeomorphic to one and the same thing. But in our case, we have some additional information, this triangulation. And this makes possible to carry out this task and to produce a local combinatorial formula for the Euler class. Okay, in Russian. So наша задача придумать алгоритм, который вычисляет по-цепь, представляющую класс Эйлера. И что важно, этот алгоритм должен работать локально. То есть если у нас есть симплекс в базе, то значение по цепи на этом симплексе должно зависеть только от того, что лежит в прообразе, вот какая комбинаторика у нас здесь в прообразе сидит. Топологический прообраз устроен тривиально. Это просто всегда одно и то же, независимо от того, какое у нас расслоение, независимо от того, какой у нас симплекс. Вот. Единственное, что отличает картинку вот для этого молодого человека и для этого, это комбинаторика, которую они видят. Окей. So let me now explain about Euler class. So let me remind you that we have a fiber bundle E by B, and well, okay, the Euler class lives in the cohomology group n+1 of the base with rational coefficients. And by definition, which I'm going to exploit today, E is an abstraction. To existence of a partial section. Section defined on the skeleton or n+1 skeleton of the base. Окей, я собираюсь объяснить, что класс Эйлера может быть определен, собственно, с этим мы сейчас и будем работать, как препятствие существованию частичного сечения расслоения, которое задано на n+1 скелете базы. What does this mean? If you have a vector bundle, then it always has sections. For instance, there is always a zero section. But now we have a spherical bundle, and this is no longer the case for spherical bundles. Spherical bundles sometimes have no sections at all. And let us try to understand why. So let us again turn to our two examples. So n equals 1. And we have a triangulated base. Now the base, let it be two-dimensional. And now let us start constructing a section of the fiber bundle, whatever it is. Let us try to construct a section starting from the skeleton of small dimension, of zero dimension, then to the one-dimensional skeleton, and so on. And let us make sure that sooner or later we find it is no longer possible. We will find an obstruction. Okay. So let us take the zero skeleton of the base, which means that we are looking at the vertices of our simplicial complex. Each of the vertices has a preimage, which is a circle, and it is very easy to construct a partial section defined on the skeleton. So what does it mean that we construct a partial section? It means that for each point on the base, we pick in a continuous way a point from the fiber. Okay, so no obstruction yet. So the partial skeleton, the partial section exists on the zero skeleton. Okay, now let's go further. And now let us extend our partial skeleton section to the edges of the base. Let us take this particular edge, and the preimage of this edge is what is just a cylinder like this, and we have already fixed this and these partial sections, and now we need to extend. And okay, that's easy. Well, more or less easy, because we can draw this way, for instance, this way, and we can do the following. We can wind the section many times around the cylinder. So there are many different ways that are not homotopic. This is important. Okay, now when we do the same with the other edges of this triangle, what we have? So we obtain a map. Let us call this sigma n plus 1, which is exactly sigma 2. So it's two-dimensional simplex, and this is the place where we expect an obstruction. Okay, so we have a partial section defined on the boundary of sigma. So we have section, let us call it S, which maps the boundary of sigma 2, which is S1, maps to S1. Let me explain. So this is the first circle. It's just the boundary of the simplex in the base, and the second circle is the fiber, because we use the local triviality of our fiber bundle, and we see that when we look at just one simplex, we may assume that the fibration locally looks like the Cartesian product of the simplex times the circle. Okay, and we have such a map, and sometimes it is not extendable to the entire triangle here, by the reason that its degree is non-zero. And so let us write the following. So whenever we have a simplex of dimension n plus 1, we associate with the simplex the number which equals the degree, of this map. It's not, sorry. It's not phi, it's S. And so for each simplex, we indeed obtain a number, which is, by the way, it is integer. And the theory says that the collection of these numbers taken for all the simplices give us a cochain which represents the Euler class. The collection of E gives us a cochain that represents the Euler class. This is important, and let us use it as a definition. So now the same in Russian. Значит, что мы делаем? Мы пытаемся строить частичное сечение. Значит, частичное сечение мы строим до тех пор, пока мы не доходим до симплексов размерности n плюс 1. Ну, на нашем игрушечном примере это просто двумерные обычные треугольнички. Там возникает препятствие к продолжению нашего сечения на весь треугольник, потому что вот есть степень такого отображения, и если она не 0, то наше отображение просто внутрь не продолжается. И давайте определим класс Эйлера следующим образом. Значит, мы берем произвольное сечение на скелете размерности 1 в данном случае, вычисляем для него значение вот этих самых степеней для каждого симплекса, и совокупность этих чисел задает коцепь, про которую просто по определению скажем, что эта коцепь представляет класс Эйлера. And it should be mentioned that the choice of the section, it produces different cochains, but all these cochains represent one and the same class, the Euler class. And the same idea works in higher dimensions. The only difference is that we need n+1 dimensional simplices here, and here, instead of 2 and instead of 1, we have n+1 and also n+1. So this is the idea, but it is not the entire idea, because if we go back to our poor guys...
No, I suppose that on the right we have n, not n+1, Sn.
Oh, yes, absolutely. Yes, that's right. Mm-hmm. This is, well, no. Here it is n, but here it is n+1, because its boundary is exactly the n-dimensional.
Yeah, of course.
Okay. This way. Thank you anyhow. Well, now what do I want to say? Let's go back to our task. So the task is for these guys to have some algorithm such that they produce something locally, because we aim at a local combinatorial formula, and to construct just one section which is constructed locally is impossible. So we plug in some other idea. So this is the main idea. Okay, assume that we have not one partial section, but several. S1, Sk are partial sections. Defined on where they can be defined, on the end skeleton of the base. And each of SIs produces a cochain. Let's call it EI. And as we know, all these cochains represent one and the same cohomology class. And therefore, if we take the average, so we sum up all these cochains, we just stupidly average them. We get another cochain, which is no longer integer, which is rational, but it also represents the Euler class. Значит, идея такая, что мы берем несколько сечений, и поскольку все соответствующие коцепи представляют класс Эйлера, мы можем всех эти коцепи усреднить, и все равно мы получим коцеп, который представляет класс Эйлера. Moreover, some extension of this idea. Let us take S1, Sk, and also S1, Sm, and also S1 prime, Sn prime. Let them all be partial sections. Then we can average in the following way. Then we take the following. So we look at the first series of sections as positive sections, and the second series of sections, let us treat them as negative sections, so to say. Let me write the formula because it will be more or less clear. So if we take the following sum, the following averaging, so here we take the cochains related to SIs, and then we subtract the cochains related to SJs prime from 1 to m, and here from 1 to n, and assume that m is not equal to n, of course, then this average also represents the Euler class. So these are trivial. And now let us so this is the idea. And well, the main idea of what I'm going to explain is that let us construct many sections, a finite family of sections, but not one. There will be many sections. And the combinatorics of this preimage dictates what sections should be constructed, what concrete form of these sections. And it would be nice to start again with our toy example. So let me quickly redraw our toy example when we have triangulated B and triangulated total space is okay, and well, let it be like this here. So here is the triangulation, and the idea is the following. So assume I am a person who sits on this.
Gaiane, it's not a triangulation, I believe.
I'm sorry. Yes, you're right. Assume I am this green person and I sit on this segment. So I follow the way I described before. So first of all, I will define my collection of sections locally. I will define all the sections locally, starting from the vertices, starting from the zero skeleton. And I decide to do the following. I take one point per a segment, exactly as I depict here. So these green points here, and for this point I take red, red, and red. So you see that the number of sections is now different. So for the left-hand side I have 3 partial sections, and to the right-hand side I have, oh well, again 3. Well, let us change it. I don't like that. So let's make this, and let us add 1. Okay, and 4 red points. Okay, now assume I take a point. Now what am I doing next? I have to extend my partial sections to the cylinder, to the edge. So I have.
Probably you need to continue one of the segments, otherwise you have a segment of a right triangle divided into
yes, that's right. Absolutely right. But well, I will focus mostly on the left-hand side part of the picture. Okay, thank you. So I have to connect. I have to extend my partial section over this segment. And what I'm doing now, so I may assume by local triviality that this green point and this red point, they sit on one and the same circle, and I connect them in 2 ways. I can connect them this way, and I also connect them this way. Of course, I can wind my partial sections many times around the circle, but I don't do this. So I do either this way on the cylinder, the picture will be the following, or, well, something like this way. I think that was correct. Okay. Well, this is what I do. So I start with these green and red points, and then for each of the 2 points, I have 2 choices how to extend my partial section. And the point is that whenever I have a choice, I use all possible choices. I use 2 possible options to connect them, and then I average. You see? Then I average. So I connect in many, many ways here, all possible combinations of red and green points. So to summarize over this segment, I have 12 pairs of red and green points, and each of the pair I connect in 2 ways. So I produce 24 partial sections over this segment. And now imagine that here on the second segment there sits another person who is carrying out the same algorithm. He will produce some other number of partial sections. But what is nice that all these partial sections, they are consistent on this boundary. Here they all are consistent. So if I have a partial section here, then it extends somehow by the second person. Also in many different ways. So I produce really many partial sections.
Гайане, а вот в слое между синим и зеленым человечками, синие и зеленые человечки, эти красные точки выбирают независимо или согласованно?
No. These points are chosen in a very special way. So you see, the preimage of this vertex, we have, so to say, a triangulated circle. So a circle cut into segments. And now the task is to take the dual subdivision of the circle and to take the vertices of the dual subdivision. So
Нет, когда сечение выбирают.
Когда сечение выбирают?
Зеленый человечек выбрал сечение, у него правый конец какая-то красная точка. Синий человечек выбрал у себя сечение, у которого левая красная точка. Они должны совпадать?
Значит, зеленый человечек выбирает все возможные... Мы же выбираем не одно сечение, мы выбираем много. И мы выбираем все сечения, которые получаются в результате вот этой процедуры, которую я только что описала.
Но тогда не всякое сечение, которое выбрал зеленый человечек, продолжается до непрерывного сечения.
Нет,
если выбрать выбор...
Максим, я так понимаю, что красные точки фиксированы до того, как выбираются сечения.
Но выбор, красные точки фиксированы. Ну
фиксировано,
вот,
да.
Ну да, но если зеленый человек выбрал одно сечение над
слой над собой, красный,
синий выбрал сечение слой над собой, то оно не будет, их объединение не будет непрерывным сечением.
Это правда, да, это правда. Вот. Но это не страшно. Значит, мы берем только те непрерывные сечения, которые получаются в результате вот таких вот склеек. So we may think the following, that there is a coin, and for each vertex of the skeleton in the base, we throw a coin, and we choose randomly the red point, and then choose randomly a green point, and then choose one of these 2 ways how to connect the red and the green point, and so on and so forth. That idea. Максим, это же твоя идея.
Я-то все понимаю, я просто, чтобы уточнить.
Да. Вот. Okay. And now let's go further. So we succeeded in extending our partial section to the one-dimensional skeleton, and now we need to compute the Euler, the co-chain for a triangle in the base. So the base is 2-dimensional. let us think so. And now, what do we have? Let us observe the following. So there is such a nice idea. Let us color the simplices which appear. So the triangles in the preimage of this segment may be colored in the following way. So these triangles are green and these triangles are red. And you see what is the rule. The rule is the following. So each of the triangles in the preimage has two of its vertices on either on the green or on the red lines. And depending on that, we color it either green or red. And if we have a point sitting here in the middle of the, just inside the edge, and you look at the preimage of X, I'm sorry, X is here, then you see a necklace, with some green and some red points. Because if you go upwards in my picture are oriented, therefore the necklace is also oriented. And how do we construct this necklace? Exactly as the picture suggests. So you go up, here you are red, then comes green, then red, then again red, then green, and then again red. So probably I depicted it erroneously, but please forgive me. Okay. So we have a triangle.
I'm sorry, Gaiane. I kind of missed it. Is the fiber just one-dimensional? The fiber is only circle. Okay.
With the circle, yes. It is a toy example. So, and we live here, and this is a triangle in the base, and now we wonder what is the average of the cochains. So what is the average degree which defines the Euler class? So this is the triangle in the base. Here we have green vertex, red vertex, and the third vertex, let it be blue. And if one takes a point X sitting inside the circle, then in the preimage there will be necessary not two colors but three colors. The blue color will also appear, and there will be two beads on our necklace. And now we know the following, that just one triple. Now, what is the task? The task is that we should go around the boundary of the triangle in the positive direction, and we have a map from S1 to S1, and we need to look how many times this section winds around our circles. It's the winding number, to count the one, to look at the winding number. And so we have three beads. When we go, say, from red to green, we know that from red to green, we know that we use either this way or this way. From green to blue, we again use either this way of extension or this way of extension. Let me just depict one. So assume that here we take this type of extension, and assume that here we take from green to blue. Okay, from green to blue, let it be this one. And from blue to red, let it be this one. Let it be this one. Then you see that this way, this combination of extensions gives us the value, the degree, which equals 0, because you see, this is the degree in this case equals 0. But there are some other cases, and there are 8 such cases, because for each couple of beads we have 2 options, and all these options have equal rights, and so we have 8 options to extend this red, green, and blue sections to the entire boundary of the triangle. And if you count in an accurate way, use each triple of bits gives us contributes either plus 1/2 as the average, or depending on the orientation of the triple. And this gives us a formula for the local combinatorial formula for the Euler class in terms of this type of neclaces. So this is here is the algorithm for a person who sits. The algorithm is the following. Please color the simplices which you see hanging above you. The simplices are colored in 3 colors, red, green, and blue. Then create the colored necklace like this. And then look how many positively oriented triples, multicolored triples are there, and how many negatively oriented multicolored triples are there, and then average them, keeping in mind that each positive triple gives us minus 1/2, and each negative triple gives us 1 plus. Алгоритм для человека, да.
One question. So, if I understand right, so to each side of the triangle downstairs, like in bottom part of your picture, like say blue-red triangle interval, right? You assign a plus 1/2 or negative 1/2.
Yes.
Sorry, not in the bottom part, but to each lift of this interval, you assign either plus 1/2 or negative 1/2.
No, I'm doing the following. So my task is that create all possible combinations of green, blue, and red, all existing triples. For each triple and for each pair in the triple. Now let's fix a triple. So the triple is fixed. For each triple, we do the following. For each pair, I connect either this way or this way. What does it mean that I connect? It means that I extend the section to the segment either this way or the opposite one. Okay, and now, so it means that for each triple, I need to look at 8 possible options of extension. Because for each pair, I have 2 options, 2 to the power 3 is 8. And now just the computation shows that for positive triple, I have this number, and for negative triple, I have this number. This is, I count once and forever, because triples are very uninteresting. They are very elementary objects. So I count this once and forever, and then I create the following algorithm. Look at the pre-image. In the pre-image, you see a necklace, and for this necklace, you should average these numbers over all existing triples, over all existing multicolored triples. Давайте скажу по-русски. Значит, алгоритм такой для этого зеленого человечка и вообще для любого человечка. Значит, алгоритм, он не зависит от того, на каком треугольнике он сидит. Значит, алгоритм такой: посмотри наверх. Значит, над тобой висят симплексы, в данном случае трехмерные тетраэдры, правильно? Значит, если у нас треугольничек в базе, он двумерный, значит, над ним висят трехмерные тетраэдры. Они все покрашены. Они все покрашены вот в соответствии с понятным принципом. Они все покрашены в красный, синий и зеленый цвета. Значит, как-нибудь, вернее, для начала раскрасить вершины своего симплекса в красный, синий и зеленый цвета. Вот, потом покрасить треугольники наверху, симплекс наверху. У тебя получится ожерелье с бусинами 3 цветов. А теперь нужно сделать следующее. По всем разноцветным тройкам, разноцветные тройки – это вот такого типа, красный, зеленый, синий. По всем разноцветным тройкам нужно усреднить вот эти вот числа. Значит, если тройка положительно ориентированная, берем минус 1/2. Если отрицательная, то плюс 1/2. Значит, нужно просто сложить вот эти числа по всем тройкам, потом разделить на общее число троек. То есть усреднить это в данном случае просто взять, смотреть, что у нас в среднем при этом получается. То есть это и есть идея усреднения. So this is the average idea, which works here very nicely. And you see that, well, it's a really local combinatorial formula, and it works. And the algorithm is, so to say, simple.
А можно замечание сделать?
Да, конечно.
Что та формула, которая получается для вот Эйлерова класса для случая окружности, которая вот только что была произведена, она принадлежит Коле Мнёву, а то доказательство, которое сейчас было воспроизведено, принадлежит мне. Так что все, что было до сих пор, это было введение, и сейчас, собственно, и начинается доклад.
Да, that's right. So the formula itself, it belongs to Igusa, Mnёv, and independently. And well, once Maxim rediscovered this simple proof, elementary proof of the formula for the S1 bundles, and Maxim gave a lecture at Dubna Mathematical School, and later on, many years have passed since that time, and then I understood that the same, almost the same, with some addenda, can be repeated for Sn bundles. So now we're looking at Sn bundles. And their Euler class. Here we start some new things. Fine. Okay, so let us try to mimic the same idea. So we have the base. This is the base, and this is a simplex in the base. Let it be just a triangle. And let us not call it, let's just put the numbers. So this is the vertex number 1, this is the vertex number 2, vertex number 3. And what we have in the preimage? In the preimage of each vertex, I have a sphere Sn. So I will depict two-dimensional spheres. The point is that for even dimensional spherical fiber bundles, the Euler class always vanishes. It is true, but on the other hand, I cannot draw three-dimensional spheres. So I will draw two-dimensional pictures. Okay. And let the point number 1, the vertex number 1, be red. And what we have here in the preimage? In the preimage, we have a triangulated sphere. This is the condition of consistency of triangulations. We have a triangulated sphere, but we remember from before that we do not take the tiling of the sphere itself. We take its dual. And in our case, let us take the dual cell decomposition. So we have some red cell decomposition of this. Point number 3, we have, well, some other cell decomposition, which is dual to the already existing. It is not very difficult to understand, but let me sweep under the carpet all the details which appear here. And the point is that if we take a point between red and white, then that the preimage of X, if we take the dual of it, it's just the superposition. So on the point, for the point X lying inside the H1, 3, we have a superposition, which means that we have something like this, which it is easy to draw, but я делаю сейчас более-менее то же самое, что я делала вот для одномерного случая. Значит, что у нас тут происходит? У точек в прообразе, значит, у вершин на базе в прообразе лежат триангулированные сферы. Но я рисую не триангулированные сферы, а их двойственное разбиение. Для этого нужно, на самом деле, скобочку замечу, кое-чего дополнительно от этих триангуляций потребовать, но вот что именно я не буду говорить. Вот. И тогда, если мы возьмем точку, которая лежит на ребре, то над ней будет тоже как-то разбитая сфера висеть, уже даже не триангулированная. Вот. Но для нее двойственное разбиение будет выглядеть как просто суперпозиция вот красного и синего. Понятно, что происходит, да? То есть просто мы, грубо говоря, мы взяли общее подразбиение, можно сказать так. Ну и, наконец, давайте это будет дорисуем.
Можно справа нарисовать, что этому соответствует в предыдущем нами изученном случае n равно единице?
Давай мы не будем рисовать, мы просто вернемся. Сейчас я поясню. So, what was that? So you see that the black points here are the vertices of the triangulation. The green points are the vertices of the dual tiling of the circle. And here again, the red points are the vertices of the dual tiling. And here, how do these beads appear? What do we see here? It is exactly the dual tiling of what we see here, of this circle. And so I also would like to draw here the and something green. There is also something green. So there is a superposition of colors, and now our is.
Сейчас, извините, можно спросить еще? Для того, чтобы нарисовать таких два подразбиения на одной сфере, вы должны как-то сферу с синим подразбиением отождествить со сферой с красным подразбиением.
Yes, you're absolutely right. Thank you for the question. So, in reality, you should first look at the point in the middle. You already have it. There are some necessary words which I did not say, which I prefer to omit, saying that the following. So the fiber bundle over this triangle is trivial. We choose a trivialization. And we have to prove, but we don't do it right now, that this combinatorial picture does not, and this, they do not depend on the trivialization. And this is more or less clear, because if you start with this and this is with the central point, with the point lying this here. And okay, let us go back. For instance, in our two example, it is more or less so the same question appears here. How do these green points and red points appear on one and the same circle? How do they interplay on one and the same circle? The answer is the following. Don't try to put them on one and the same circle. Just take a point and go in its preimage. And then you see that it is already there. So the order of red and green points is already given by the looking at preimage of the inner point.
Но это значит, что ваше отождествление на самом деле определяется триангуляцией, да?
Конечно, да. Вот это отождествление, давайте я скажу по-русски, потому что, значит, вот эта картинка сложная картинка, она происходит из анализа прообраза точки, которая лежит строго внутри треугольника. Конечно, если вам отдельно выдадут синюю картинку и красную картинку, то их друг на дружку можно наложить сотни разных способов, совершенно не обязательно таким. Вот. Но вы точно знаете, какой у вас есть способ. Просто можно идти в другом направлении, что у вас есть цветная картинка, а когда эта точка внутренняя идет, скажем, к вот этому ребру, то все зеленое надо стереть. А когда дальше мы идем к красной вершине, то все синее надо стереть. Как-то так. Okay.
А если у нас есть симплекс, который при проекции на базу у него, сейчас скажу, он лежит, например, над стороной, и у него схлопывается что-то над зеленой и что-то над синей, то куда его относить?
Да, бывает. Вот посмотри, вот он здесь есть. Сейчас я тебе его покажу. Вот посмотри на эту точку пересечения. Вот это именно такой симплекс. У него что-то над зеленым, что-то над синим схлопнулось. Потому что у нас же двойственная картинка. So this picture is dual to the initial. All the vertices here correspond to the top dimensional simplicity. In particular, this point, which is neither blue nor green. It is exactly the one you are interested in. So they exist. Yes, create no harm, so to say. So we know that they exist. Okay, now let us create partial section. And let us follow the pattern of our two example, meaning that, so we start with the zero-dimensional skeleton. And for zero-dimensional skeleton, this we do absolutely the same. So we take the blue point here, and as a collection of partial sections, we take all the vertices of this cell decomposition. For the red vertex, we take all the vertices here. For the green vertices, all these vertices, but we know we never take this vertex. Okay? Well, now, let us assume that a red vertex and a green and a blue vertex are fixed. Let me fix two vertices. Say I fix this vertex and I fix this vertex. Now comes the most interesting thing. So now I wish to extend my atom, which is defined over these 2 points, and my task, my local task, is now to extend it over this segment. This means that I need to, each extension to the segment creates a path here on this sphere. And there are very many paths. And so the idea is first to agree that our extension should go along the edges. So let us think that our bundle is two-dimensional, that n equals 2, along the edges of this complex. And even so, there are many paths leading from this point to this point. And we need only finite number of options to connect these 2 points. And now here comes the idea. The idea is to use harmonic chains. In simple words, this means the following. Let us take an electric battery. And I plug minus here to the blue point, and plus I plug here. And then there arises a path, some electric current. Well, it's not a path. It's some electric current leading from here to here. And I also assume that all the edges which you see here, they are they have one and the same resistance. They have one and the same resistance. So there will be some electric current. It will be not one path. It will be a linear combination of paths. So it will be a linear combination of sections. But to this electric current, which you see here, we should look at the at the one chain of the complex well, let us fix some notations. So this is the point number 1, and this complex is gamma 1. And this complex is gamma sub 1, 3. So what we see, this current is a one chain of the complex gamma 1, 3, and it possesses the following property, that the boundary operator of this current equals exactly V1 minus V3. So let us look at this. This is V3, this is V1. So this guy is a zero chain, is a closed zero chain, and we need to find another chain, one chain whose boundary equals this closed chain. Okay, that's the idea.
Можно еще раз? Если у нас если сферы n-мерные, то...
Если сферы n-мерные, мы делаем... Есть теория, которую сейчас расскажу.
Сейчас у нас n равно 2 всегда, пока? Или что?
Пока у нас n равно 2. Но мы должны будем перескочить, потому что нам нужен общий случай. Ну и вообще.
Здесь n равно 2. Хорошо, хорошо.
Пока, когда n равно 2, то достаточно... So for the dimension n equals 2, and when we talk about extensions over edges, actually it is for any dimension. If we talk about there exists a nice intuition coming from electric current. Значит, у нас есть такая вот интуиция, которая приходит из электрических цепей. Запускаем ток как-то течет из вершины V3 в вершину V1, и тем самым у нас вот это вот течение тока можно разбить в комбинацию, в линейную комбинацию каких-то путей, ведущих из V3 в V1, ну, с рациональными коэффициентами. Вот. Хорошо. Now a little bit of general theory. Let me see what's the time. No, I have still time. So general theory.
Сейчас, а в случае даже n равно 2 еще не закончилось. Мы же должны построить...
Да, не закончилось. Мы пока...
цепь.
Правильно, должны. Мы еще пока не строим. So the first task is to extend our section from zero skeleton to the one-dimensional skeleton. And this task is not yet completed. А то он будет как вот последний шаг, он просто другой. Поэтому так давайте вот в той последовательности, которую я буду рассказывать. Okay, so we assume that we have gamma, which is just a simplicial complex. Fine.
Простите, можете повторить, а то ничего не слышно было.
Let gamma be a finite simplicial complex.
Спасибо.
And, well, denote by CK the K chains. Or what does it mean? That this means that we consider all linear combinations of k-dimensional simplices of gamma. This space, not as a decay, is, let us identify it with, we take only rational coordinates, as q taken to the power of k cells, k simplices. And it is instructive to think of it as a vector space with scalar product, with a natural one, meaning that each k simplex corresponds, so all k simplices, they correspond to orthonormal basis. Okay, and we have boundary operator, which maps ck to ck minus 1, as everybody knows. And related to this scalar product, we may create the adjoint operator, which maps from ck minus 1 to ck. And we also may create this discrete Laplacian, which equals d star plus d star d. And we say that a chain, this is the definition, a chain A is harmonic, and it is in all dimensions. It's harmonic if delta A vanishes. And the crucial property of this discrete Laplacian is the following: that each homology class has a unique harmonic representative. Has a unique harmonic representative. This is important because we aim at uniqueness. We aim something should be uniquely defined, maybe in several ways, and then we average. And this theorem allows us to work further. So this is our first new idea: use harmonic chains.
Дельта А равно нулю влечет, что и ДА равно нулю, и D со звездочкой А равно нулю.
Yes, that's true. So for harmonic chains are closed. Okay. This was the first idea, and the second idea, which is new, is the following: that one can work, one has right to work with chains rather than sections. Let me explain why and what do I mean. Okay. So let us come back to this picture. So our task is to extend this section to the edge, to this edge. If we extend it to a unique section, then we get a path from this point to this point, some path. And what we propose that is, instead of looking at paths, we look at one chains, and these are different things. And it is true that each one chain is representable as a combination of paths. But the problem might be that this representation is not unique. And it is also true that in higher dimension, it is not clear at all why a chain can be represented as a linear combination of sections. Okay, so well, what would be interesting? I have approximately half an hour. Is that true? Left. Who is in charge? How much time do I have?
Less, yes.
Okay, so let me say some important words. Still, let me spend some time in expressing this idea. So we need some, I will not prove these facts, but I will just mention them. So assume that we have a section, meaning that we have a map from a k-dimensional sphere to k-dimensional skeleton of a cellular complex gamma. Gamma is a cell complex which is topologically an n-dimensional sphere. Whenever we have a map from sphere to the skeleton, then we automatically have a chain, a closed chain, which we denote this way, and which is a chain which lives where? In k-dimensional chains of gamma integer ones. Is that true? That's true. Okay. Let S tilde be a map. So all the maps are continuous from the disk to the skeleton k+1 of gamma, such that S tilde on the boundary of the disk equals S. Then it gives rise again to a chain which is no longer closed, which we denote like this, and it is the chain of dimension k+1. And it is clear that if we take the boundary of S tilde, we get exactly the support of S. Okay? Let us call such chains as S chain. So it is an S chain. Okay, once again, if we have such a map, then we have a closed chain sitting here, but not vice versa. If we have a closed chain, even with integer coordinates, it's not clear why does it originate from some map S or not. And the same for S tilde. But the following lemma holds. Let A equal S is supported by some map S, B and S chain. And let B is a chain, just a chain, such that the boundary of B equals A. Then B is not necessarily arises from some S tilde. This is not true in general, but B is an average of S patches of A. That is, there are several SIs and SJs tilde, such that SI and on the boundary equals S, and ISJs tilde also equal S on the boundary, and B is the average in the sense we are going to use. So it is 1 over M minus N the sum of SIs from 1 to M minus sum of SJs tilde from 1 to N. Sorry, I'm not accustomed to give lectures in Zoom. I already forgot how to do it. Well, so this is the formula which enables me to forget about sections and to work with chains only. Okay, now let's go further. Assume that it is not S2, assume that this is S3. And we already fixed some red point, some blue point, and there is also some green point. So my task now is to extend my section So I have my section defined over the one-dimensional skeleton, and now I am aiming at the two-dimensional skeleton. Now what do we have? So this is the first, so now we have 3 points, and we already have, well, chain connecting red and blue point, the chain. It is not one single path, it is an average of paths. But I depict it as a path, and chain connecting blue and green point, and another chain connecting these 2 points. Taken together, they form a, so let me put here numbers, V1, V2, and V3. And for instance, here we have not one section, not one path, but a collection of paths, SIs and SJs tilde. The first ones are positive, the second ones are negative, and this is the average of this section. So to say, you cannot average, so this is the problem, that we have no right to take average of sections, but we have a complete right to take average of chains. This is a chain, and this is also a chain, and this is also a chain. But still, we know that there are sections, so we can work with chains, but keep in mind that behind our action there is an extension of sections. And now what we do, this is a closed chain, and we need, now our next task is to extend it to another section. And again, this can be done in many ways, but somehow to extend it to a map from the disk to the sphere, and we do it using, we extend, so the idea is the old one, extend this closed chain using harmonic extension. Okay. Well, and we act this way. Sorry. We act this way until the very last step, when we arrive at an n-1 dimensional chain at n-dimensional sphere. So this is the n-dimensional sphere, and we have an n-1 dimensional chain, which is closed. And now let us again look at a toy example when the sphere is two-dimensional and we have some closed chain with dimension 1, and we may imagine that we have something like this. And here is a kind of shortcut. So at the very last step, we don't need to use harmonic extensions. Instead, we use the third idea, which simplifies the life. Use winding numbers. So this is the two-dimensional sphere. Just imagine that there is just a curve like this. So that our n-1 dimensional chain is just a curve. How do you extend it? In the sense that you need to, so we look at this chain as a map, as a section from S1 to S2, and we need S tilde from D2 to S2, such that S tilde restricted to the boundary of D2 equals S. So we have a map from the circle to the sphere, and we need to extend it to the map from the disk to the sphere. And there you do not need advanced ideas. You just observe that it can be done also in many different times, in many different options. But, if you pick a point and you want this extension to be 0 at this point, then the value of the extension considered as a chain is easily recovered. So it's just a winding number. So you go on the surface, and once you cross it, it becomes 1 here. It becomes becomes 2 here, and it becomes -1 here. So this curve cuts the sphere into domains, and on each of the domains we have one and the same number, which is just the winding number or crossing number. Well, that's easy. Okay. Now let me formulate the. Let me stop sharing this. Sorry. Let me stop sharing this, and let me show you here. Here. Just a moment. I have technical problems. How do I make full screen? Ага, просмотр. Кто-нибудь мне может подсказать, на что я должна нажать, чтобы у меня стало большое?
Выбор, у вас есть выбор полноэкранный режим, Ctrl-L.
Так, сейчас. Ctrl.
Нет. Да.
Стало совсем плохо. Нет, все, хорошо. Хорошо. Okay. So eventually, what this is, now I am ready to formulate the result. Not the proof, but the result. So eventually we arrive at the following algorithm. Here is the algorithm which produces a chain, a cochain. And here is the theorem saying that this cochain represents the Euler class. And I'm not sure that it is, oh my goodness. Sorry. Well, I don't dare to type further. Так. Значит, сейчас я собираюсь вот рассказать, как выглядит алгоритм. Видна вот такая ручка? Видна. Хорошо, значит, как выглядит алгоритм? Что нужно сказать вот этим человечкам, которые сидят на симплексе? Значит, so how does the algorithm, the final formula look like? So there are some small persons, each sits on his own simplex, n+1 dimensional. And each of these persons needs to produce a number, some rational number, which will be assigned to the simplex. And here is the algorithm. Okay, take the simplex. Denote its vertices by some numbers enumerated. And now look at the preimage and these colored pictures that we have seen. And in the preimage of each of the vertices, there are many colored vertices, and all possible combinations of these colored vertices should be treated. Assume that one combination, which is n+2 tuple like this, is fixed. Now what we do? So the first step is to extend our section on the one edge. But instead of speaking of sections, we speak now about chains. And so we take the harmonic extension of the zero chain like this, and we create a chain which is now two-dimensional or one-dimensional, which we define this way. On next step, as I depicted, we take triples of these chains, and they create a closed chain, and we again take harmonic extension, and we proceed further on in the same manner. So there is a formula which is long and nasty, but still we do basically one and the same. When we need to extend, we use the harmonic extension. And harmonic extension is motivated by this electrical current, which gives us some chain, not section. But we always keep in mind that sections, they do exist. And the last step is quite a simplification. It is different because we may apply this winding number idea. And on the last step, what is good on the last step, that very many numbers, they cancel out, and finally we have a number. I remind everybody that this number is responsible for the degree of the boundary of the simplex. We get a chain which encodes the degree of from the boundary of the simplex to the n-dimensional sphere.
Яна, извините, а можно попросить повторить еще? Как вы определяете это harmonic extension?
Harmonic extension я замела под ковер, но я про это скажу. Давайте я закончу с этой формулировкой.
Спасибо.
С формулировкой. There is a theorem which says that eventually we arrive at some cochain, which is a closed cochain. It's easy to see. And this cochain, so the final step, this cochain over all possible tuples of the vertices in the preimage of the vertices of the simplex. So more or less, this is the end of the story. I don't want you to look at the details, but the idea is the following. So we don't know how to extend section, but we know how to extend chains in a harmonic way. And we do it further and further and further. And finally, we arrive at something which gives us a number. There is a formula for this number. Here it is. And that's it. So that's it. This is the formula. Окей. Теперь по-русски. Значит, вот алгоритм, который вы видите, который написан или не видите, потому что очень мелко, но вы можете его прочитать, значит, ссылка есть в анонсе. Он говорит следующее. Значит, когда вы сидите на n+1-мерном симплексе, какая ваша цель? Вам для этого n+1-мерного симплекса надо раздобыть рациональное число. Ну, что вы делаете? Значит, вы должны посмотреть в прообразы вершины, увидеть там цветные точки и набрать все возможные наборы цветных точек. Теперь, значит, какой смысл пункта номер 2? Мы продолжаем наше сечение. Вот этот пункт номер 1, он фиксирует сечение на вершинах нашего симплекса. Теперь продолжаем наше сечение на ребрах. Мы это делаем с помощью подключения туда батарейки. При этом мы получаем цепь. В гомологическом смысле цепь. Не путь, не сечение, но цепь. Но мы уже себе доказали предыдущими рассуждениями, что мы имеем право работать с цепями, а не заморачиваться с сечениями. Сечения есть. Нам достаточно знать, что они есть, но мы про них не думаем для алгоритмов. Да, в алгоритме они нужны. Вот здесь это упрощение, что нам можно не думать про сечение. Вот, потом, значит, мы продолжили все на ребра. Теперь нужно продолжать на двумерные симплексы. У двумерного симплекса 3 ребра. А у каждого ребра вот есть такая штука, которую мы получили на первом шаге. Значит, опять у нас есть некоторая замкнутая цепь, берем ее гармоническое продолжение. И так далее, и так далее. Последний шаг, он немножко другой, ради того, чтобы у нас много чего сократилось, оно сокращается. Ну и в конце концов мы получаем число, примерно в таком же смысле, как и вот в игрушечной нашей модели. Вот. Ну и вот теорема, что совокупность этих чисел, значит, у каждого симплекса получается, есть рациональное число, значит, это некоторая коцепь нужной размерности. И утверждение такое, что эта коцепь, она представляет класс Эйлера. Она является представителем класса Эйлера. Вот. So that was now I return back. I'm sorry. У меня планшет, но поскольку у меня времени мало, давайте я здесь порисую. Да, уже совсем мало времени, поэтому я здесь порисую. Это будет некрасиво, но ничего. Что такое? So I was asked a question about harmonic extension, to give more details about harmonic extension. Just a moment. Okay. So we have a sphere. And we know that we have a discrete Laplacian. And we know that each homology class is uniquely representable by harmonic chain, by a harmonic chain. Now,
сфера триангулированная, да?
Не триангулированный, это клеточный комплекс. У нас не триангулированные сферы, это хороший клеточный регулярный. So sphere is a regular cell complex. Not a triangulation, but because it is dual to something, it's not triangulation. Well, let me somehow draw some nice cell complex. Okay, and we have a closed chain. So this is Sn. And we have a closed chain. A is a closed chain. In our very first example, it was zero-dimensional closed chain. That is the difference, homological difference of two vertices. And we need a unique to find unique, in some sense, chain B, such that the boundary, the B equals A. In very simple words, we need a path from one point to another. And what happens here? So this, well, there are no one-dimensional homologies for the n-dimensional sphere. And so it seems that the general theory is inapplicable here. But we do the following trick. I take the sphere and I attach to these points a segment. So it is a sphere with a handle. It's not a handle, it's just a segment. So I get a topological space which has homologies, and its homologies is Z. So if I have a chain which is closed, and the value of this chain, I'm sorry, the coefficient of this chain on this handle equals 1, then there exists a unique chain B tilde, which is a chain with respect to this new topological space, such that the value of B tilde on this handle equals 1, which is harmonic. So we apply, in other words, we apply the theory of harmonic chains not to the sphere itself, but to, well, to some new topological space which we create. And this idea,
А если даже вот в этом случае, если А не состоит не из двух точек, а там несколько точек, взятых с рациональными коэффициентами, так что в сумме равны нулю коэффициенты. Нужно много дужек приделывать тогда.
Yes, so there is a general, there is a general idea. The general idea is the following, that you take the corresponding skeleton, the cone over the skeleton, and you patch the cone over skeleton to the sphere. Немного-много дужек. So in this case, you take немного-много дужек and something like this. Something like this. So you take the skeleton. I'm sorry, it was my tablet plugged out of the conference. Well, Maxim, more or less you are right. But there are some details that you take the cone over the skeleton, and so эти дужки, они должны здесь иметь...
Да, я увидел все. Это меня удовлетворило.
And this idea works with not only the zero dimension, but for bigger dimension as well. So you have to patch a cone over the k-dimensional skeleton and work with this topological space, and then you win. And so this is the harmonic extension. So there exists. Well, let me take the pointer. So once again, we had a closed chain A, and we wanted to define a chain B in a unique way, such that the boundary of B equals A. And this is the idea that you take a harmonic chain, which is harmonic with respect to a bigger space, to a bigger topological space, not to the sphere, because on the sphere there are no harmonic chains. They are all zero. And so this is B tilde, and then you take B tilde, and then you forget this superfluous handle from B tilde, and what you have is exactly B, and it is also possible to write a formula. So this B, it equals, so that's a simple formula, is equals the following. So you take delta, and you take the adjoint D star of A. So this is the formula. Do you see that it is unique? Well, now there are many subtle things that you should keep in mind, that whatever you do on the edge, so imagine you treat one single edge of the base. One single edge serves as an edge for different simplices. There are different simplices that are adjacent to this edge. And this manipulation, it depends only on the combinatorics of the preimage of the edge. So this all is correct, meaning that all these sections, they are patched together. They have this procedure, this algorithm I presented is consistent on the simplices that are adjoint to different n+1 dimensional simplices. And this is all true. This is all true. And what I also would like to mention is that there is a lot of room for improvement, for changing the formula. Because, for instance, on the step number 1, when you need to connect, when you wish to connect 2 points on the sphere by a path, for instance, you could apply some other idea. For instance, you could choose the shortest path connecting these 2 points. Of course, sometimes there are several shortest paths. You cannot choose one of them canonically. In this case, you take just average. Take the average of the shortest path and so on. The other idea is that when you take this adjoint operator, this adjoint of the boundary operator depends on the scalar product which you define, which you set on the space of chains. And there exist different scalar products, as you know. So there is some room for creating other combinatorial formulas. So to say, this formula is not unique, but it can be, other formulas can be created in this spirit. And the final remark that if you apply all what I have told you today to the one-dimensional case accurately, then you obtain the same formula as was the Mnёv-Sharygin and the Igusa formula, which was discovered by Maxim Kazaryan. Well, and I think that I stop here.
Хорошо, Гайане, спасибо большое. Время действительно заканчивается. А у меня вопрос. А были ли попытки довести до практики, в каких-нибудь примерах посчитать или что-нибудь, какие-то для каких-нибудь картинок сказать, чему он равно? Такого рода вычисления проделывали?
Вычисления есть у Коли Мнёва для расслоения со слоем окружности.
Нет, это я видел. Там у него это палиндромы всякие, да, это я видел. Хорошо.
Вот. А я с расслоением со слоем окружности мы посчитали со слоем окружности, это тавтологических расслоений над пространством модулей. Мы там посчитали, как выглядит класс черно. Там получается, это как раз мы в каком-то смысле тоже переоткрыли формулу Игуса, другую, но, в общем, там получается, для пси-классов. Там это как раз было очень удачно применять вот формулу для S1 расслоений. А для этих я только вот недавно это все сделала, записала, и, в общем, только недавно написано. Пока нету.
Понятно. Хорошо, Гайане, у нас еще будет много вопросов, но я думаю, что мы будем тут в узком кругу еще это изучать, и еще к тебе обратимся за разъяснениями.
Спасибо большое. Да, я буду очень рада, если будут вопросы. Я с радостью буду общаться. На самом деле я хотела лично приехать, но сейчас как-то не располагает.
Ну, еще будет возможность.
Угу.
Ладно.
Спасибо.
Хорошо.